Okay, so here we're going to take a look at the reaction of carboxylic acids. And first of all, we're going to start over here with their formation. So we've seen this process previously in our reaction of alcohols poster, where one way of making a carboxylic acid is to oxidize the primary alcohol. And if you remember, we use acidified potassium dichromate, Cr2O7 2 minus, in acid, H+, and we will be able to oxidize that primary alcohol, ethanol in this case, to our carboxylic acid. And remember, carboxylic acid has that C double bond O OH grouping. And in this case, we're going to form ethanoic acid. There we go. So ethanol becomes ethanoic acid. Now, the ethanol is colourless, and so is the ethanoic acid. The only way you'll know this reaction is happening is because the potassium dichromate gets reduced itself from oxidation state +6 to oxidation state +3, and so we see a colour change there from orange to green. So primary alcohol heated with an excess of potassium dichromate under reflux. We can see the reaction proceed as that orange dichromate is reduced to the green chromium 3. We can do the same with an aldehyde, which is a slightly more oxidized version of a primary alcohol. And again, the aldehyde is treated with an excess of acidified potassium dichromate under reflux. And this aldehyde here would be called ethanal. All aldehydes ending in AL. And that would form our ethanoic acid again. Here we go. And again, we'd see that orange to green colour change as the potassium dichromate was reduced. Ethanoic acid being formed again here. So that's the main way of forming carboxylic acids. Once we've formed them, what can we do with them? Well, because they're acids, we can carry out acid-base reactions with them. So being effective proton donors, that's what acids are, carboxylic acids can react with proton acceptors, bases, such as hydroxides, carbonates, and hydrogen carbonates. And we'll have a look at an example of each of those here. So with sodium hydroxide, so there's our base, there's our acid, we're going to form a salt and water. And the salt in this case would be called sodium ethanoate. So there's our ethanoate ion. And here's our sodium ion from the sodium hydroxide. And then we've lost the H from the acid and the OH from the sodium hydroxide, so they'll get together to form some water. Here we go. So for those of you who like your colour coordinating, so maybe we can show sodium hydroxide here. There's our sodium, and part of that, if you prefer, I can show that like this, can write the water like this. Then the OH part of that water would be there. Whereas the H part of the water has come from the acid. So no observable reaction. You don't really see very much going on. You might see a rising in temperature ever so slightly, but these are all soluble. Sodium ethanoate would dissolve in the water, and we wouldn't see anything particularly exciting in that reaction. With carbonates, though, you would see something. Because it's a carbonate, you would see fizzing because carbon dioxide would be formed. So in this case, we've got an acid and a carbonate, and if you remember from your GCSE days, that would give you a salt, water, and carbon dioxide. So the salt in this case then would be our sodium ethanoate again. We would form water again, but this time we would form carbon dioxide, and because that's a gas, we will see bubbles of that being formed. So you'll see fizzing in this one. So if we can do our colour coding the best I can here, So I'll mark that proton there, would be one of the water protons. Then there's the sodium there. Now, those of you eagle-eyed amongst of you might be thinking, hang on a minute, there's two sodiums here and you've only shown one there. That's because we need to balance this reaction. So two sodiums there means that we would form two of these. And if we're going to form two of these, we are going to need two of these. I think that reaction now is balanced. Now, with hydrogen carbonates, similar thing would happen. We've got a carbonate grouping here, and so we're going to form carbon dioxide gas again. And so we form our salt. O minus Na plus. We'd form our water. And we would form our carbon dioxide. And again, you'd see that as bubbles. Now, balancing wise, this is a bit easier. Only one sodium there, only one there, so that's all balanced there now. Now, you can see this is highlighted. This reaction is often used as a test for carboxylic acid. To be honest, this one is as well. Both of these, if you think you have a carboxylic acid, add either sodium carbonate or sodium hydrogen carbonate solution to it, and if you see some bubbling, then that means you most probably did have a carboxylic acid on your hands, and that's used as a test. I think that's all we need to say about that. You might want to know that this is called, the same product all the way through here, isn't it? Sodium ethanoate. Okay. Right. Now then. Formation of esters. Now, esters are often characterized by sweet-smelling compounds. If you buy a perfume, it'll most likely be a mixture of different esters. Sort of characteristic, very simple ester smell is like a fruity aroma. It's often referred to as pear drop smell, which are sweets that we once sold in shops when I was kids anyway. Okay, what do you need to make an ester? Well, you will need an alcohol and a carboxylic acid. Okay, join those two together. All right, the product is an ester, and the sort of characteristic grouping of an ester is R, representing a carbon chain, C double bond O, carbonyl group, O. Now we've seen this happen, type of grouping quite a lot. If there was a hydrogen on the end here, it would be an aldehyde, a carboxylic acid rather. If there was a hydrogen instead of the oxygen here, it would be an aldehyde. If there was another carbon chain stuck directly onto this, it would be a ketone. But for an ester, you've got this grouping. So think of it a bit like a ketone, except we've squished an oxygen in there in between the carbonyl and the carbon chain. Conditions to get this to happen: reflux, the alcohol and carboxylic acid with conc sulfuric. Reaction type, because we form water in this process, it's often referred to as a condensation reaction. And the purification of the final product is by distillation. I'll talk more about that in a minute. Okay, so I've got some reactions lined up here so that we can see what happens when an ester is formed. So I always advise students to draw the alcohol first and then the carboxylic acid and point the OHs at each other. Reason for that being we can then loop them around quite easily to show the water being lost. So for this particular case then, we'd have the ethanol part first, but it's not ethanol anymore because it's about to lose the H. So the O then is now bonded straight onto that C double bond O, and we've got the end of that there, and we've also formed water here. Okay, now what is this called? Well, this was ethanol, and this was ethanoic acid. The ester will be called ethyl, from the ethanol, ethanoate. Ethyl ethanoate. If you come back to here, you can see how this was sodium ethanoate. Now that ethanoate grouping is there, but here we haven't got sodium, we've got an ethyl group on it. Sodium ethanoate, ethyl ethanoate. So we can do the same for these. So here our alcohol is methanol. So you might be guessing to yourself what the name of this ester is here now before as I draw it on. So here's the alcohol part of the ester, and here's the acid part of the ester. And again we'll form water here. And so that was methanol, and here's ethanoic acid, and you guessed it, methyl ethanoate. Now it's a lot easier to name these if you've drawn the alcohol out first, like I have here, and then the acid. Methyl, the alcohol part, comes first, then the acid part, with anoate at the end. And then the last one, we'll loop these around again to show water being lost. So this time we've got our ethanol part first, so this is our ethyl section of the ester. And here's our methanoic acid. No, sorry. Yes. Oh, too many. Hydrogen. My bad. Getting a bit carried away there. And H2O. So ethanol would make this first part ethyl. And then methanoic acid, short as possible carboxylic acid, would make this methanoate. Ethyl methanoate. There we go. Right, now, when you've made them, you can purify by distillation. So here's a distillation setup. So if we label this up, we can see down here we've got our, this will be our alcohol and carboxylic acid. And ester mix. So you're going to get a mix of all three in there probably at some stage. You can heat that up with a hot plate. Remember, never a Bunsen burner in organic chemistry. These compounds are far too flammable. And the idea here again is this has got an OH group, this has got an OH group. That means that will have hydrogen bonding with this one and with a neighbour. So the boiling points for these will be rather high. But this now, the ester has lost the OH groups, and so the boiling point is lower, and it should boil off at lower temperatures than these. So as it forms, it should boil, hit the still head here, move its way into the condenser, cold water going in here, hot water coming out here. It'll be hot, but it'll be a bit warmer probably. And then condensing ester there, hopefully. And then our pure ester in here once it's dripped into the beaker. So distillation can be used to separate organic compounds which have different boiling points. Explain how this technique works to separate esters. So first thing to say is alcohol and carboxylic acids have higher boiling points, BPTs, a bit lazy, than esters. Ester will boil first as it's formed. Move up into still head, this bit here, and condense in the condenser. There we go. Carboxylic acids in 16, just over 16 minutes. So hopefully that will make sense.